Another thing to talk about with gases is diffusion and effusion. Diffusion is, I think, more practical, but diffusion is when you have two gases and they're separated by a semi-permeable membrane. And it's really hard to keep gases from each other. So what usually happens is there's some kind of small hole somewhere in the membrane, all right? And what that means then is the gases start mixing with each other. So diffusion is if you have a gas on both sides of the membrane, and diffusion represents then how they begin to mix together. Effusion is when you have a gas on one side of that membrane and a vacuum on the other. And again, almost inevitably, you have some kind of a pinhole, some kind of hole in the membrane, which allows the gas to slip into the vacuum. So effusion, you've got a vacuum on one side, and diffusion just means you have gases on both sides of your barrier. Molecules will effuse and diffuse at a speed, and a speed you can relate is basically how many moles are going through per unit time. So let's talk about that part a little bit. Rate is like a speed, and instead of talking about speeds in miles per hour, these kind of problems, we usually think about them as how many moles of a gas get you through per second or per minute, something like that. But the rate does depend on some other stuff. It depends on the temperature, so it'll be faster at warmer temperatures and slower at colder temperatures. And big molar mass gases don't get through those holes as fast as light molar mass gases do. So as the molar mass goes up, your speed of mixing, diffusion, effusion, whatever, will go down. And conversely, small molar mass gases will mix, effuse, diffuse a lot faster because they have smaller mass. So if you were comparing helium and oxygen, and again, helium about 4 grams per mole, oxygen about 32 grams per mole, well, oxygen is a lot bigger. So it will go a lot slower than helium. Helium is smaller, it'll effuse more rapidly than oxygen, assuming it's the same temperature. On the right-hand side, you can see an example with bromine. Bromine is kind of a brownish yellow gas, and it's initially in that small Erlenmeyer, but it begins to break out. I don't know if that's a diffusion or effusion, but whatever, it's getting out into the big thing. Looks like they actually took the top off, so that's no problem. Anyway, then after a while, the gas is completely distributed through the volume of the container. Looks kind of cool. Graham's law is what's used to describe the speed of effusion and diffusion of gas molecules. And the equation itself is kind of funky. The speed of A divided by the speed of B, and again, scientists use rates usually instead of speed. But anyway, it's equal to the square root of the molar mass of B divided by the molar mass of A. So we talked about how the speed is inversely proportional to the molar mass. So that's why the rate of A is in the numerator and the molar mass of A is in the denominator on the other side. But anyway, we won't really use this equation per se, but you can. It's a way to relate the rates of A versus B, and you can do that by taking the square root of the comparison of the molar masses. This is kind of a cool experiment. It puts this all into perspective. This is a classic YouTube, right? And this isn't the cool YouTube where you watch videos of your cats making funny sounds and stuff. This is a true YouTube made of glass, all right? And on the left-hand side of the YouTube, you have ammonia, NH3, and on the right-hand side, you have a little thing of hydrochloric acid, HCl. And both of these substances can be made into a gas. All right, so we're thinking here about gaseous NH3 on the left and gaseous HCl on the right. They're on opposite sides of the tube. When the gases meet, they're going to make the solid ammonium chloride, and ammonium chloride is kind of a white solid. So wherever they mix in that U tube, all right, you're going to start seeing a solid. And the question is, like, where will the gases meet? And you can actually answer that. Ammonia, NH3, the molar mass is about 17 grams per mole. HCl, a hydrogen and a chlorine, if you look on the periodic table, is about 36.5 grams per mole. So comparing those two, HCl is a heavier gas and ammonia is a lighter gas. Lighter gases move faster than heavy gases. So what we would expect expect the ammonia to get to the halfway point faster than HCl. HCl is bigger. It takes more energy to get up to the top. So when the solid white NH4Cl forms, it's probably going to be on the HCl side. And that's just because little ammonia goes faster than big HCl. So you can see how this can be kind of cool from a perspective of a chemist. So in this problem, the ammonium chloride forms closer to the HCl end of the tube. And again, it just comes down to the fact HCl is heavier than NH3. So the NH3 zips to the top and then it falls down easily to the other side. We expect the white solid to be mostly on the HCl right side.
On the right is HCl gas, and on the left is NH3 gas. Where the two meet, a reaction occurs producing ammonium chloride gas. The reaction occurs primarily on the right because NH3 is lighter and diffuses faster.
Some of the HCl probably did have enough energy to go to the ammonia side first, all right? But most of it, by far, is on the right side. And the part that we can visibly see, which is going to be many moles interacting, definitely all on the right side.